Last time we introduced the notion of differential of a function, which is what takes us to the definition of cotangent bundle and differential forms. So let us recapitulate a little bit. You consider the tangent space and the dual of the tangent space, which is a set of linear maps on Tp, from Tp to R. And the differential is the linear map that associates a derivation x with this object, df of x, which is obtained by acting with the vector field x on the function f. We have seen that dxi locally are a basis of the cotangent space in P, but very easily you can extend this everywhere locally, which means inside the open set to which P belongs. Different story is instead to extend this to the entire manifold, and for that you have to specify what happens in the intersections between charts, which is the change of coordinates. I think you guess where we are going with this, but let's do it anyway. So, change of coordinates. So let's consider any change of coordinates from x to y, and we have some relations like this. The differential dxi on the derivation partial over partial xj is equal to delta ij, of course. By definition, we have seen this the other time. And the same thing here, you can write it like this. And you can also write it by exchanging the two indices I and j, because this is symmetric. Another obvious identity is that delta ij is equal to this object, because it's equal to the Jacobian times its inverse. That is another obvious identity. Another identity is that dyk acting on d over dxj is equal to what? To do this, it's sufficient. So we want to act with a differential in one coordinate, y, on the basis of derivations with the other coordinates, x. Well, we treat it as the definition prescribes. This yk is the function f, yk, and d partial over partial xj is the vector field x. So this is f, this is x, so this is df over dxi x. This is the definition. F is yk, so let me write dyk divided by dx, partial yk divided by partial xi, times dxi acting on x, but x, the derivation x is just partial over partial xj. And that is delta ij. And so the conclusion is that this object is dyk divided by dxj, which is what we want to use there now. So let me write this as dxi partial xi divided by partial yk. And instead of writing partial yk divided by partial xj, I replace this with this object. Yes, no equal, but just that. So now you have the change of coordinates because it's sufficient. You see delta ij is also this object here, and this object here tells you what dy I is acting on this derivation. Sorry, dxi acting on this derivation, which is the same derivation here. So you equate these two expressions, and you drop the derivation. And what you remain is with the equation of these two things, the equality of these two things. So dxi is equal to what you expected. And exchange y and j, of course, you have also this. So this tells you how to make a change of coordinates on differentials, and therefore define some objects that now we will define on the manifold. So cotangent bundle What is a cotangent bundle? It's denoted by Tm star, and as before, it's the union for all points of the manifold, which is called base manifold, as before, of the cotangent spaces Tp star. And as before, we can easily describe how it works locally and in the intersections of charts, because locally we will use the coordinates of the base, time, and the list of, let's say, components in the cotangent space of any element of the cotangent space using the basis dxi. So that means basically that this element of the cotangent space is the sum of the differentials dxi. And in the same way as for the tangent bundle, we used the letter ai, partial divided by partial x, tangent space. So tangent space means vectors, derivations, differentials are one forms, elements of the cotangent space. This is a 1,4. It is a differential form of degree 1. Actually, to be precise, let me not use, it's too early to use this terminology, so let me first say that under a change of coordinates, what happens under a change of coordinates. We have omega I dxi, which can also be written as dxi partial xi partial yj dyj, and so you can call it omega I prime dy I, and this gives you the transformation rule. This is not the differential form yet, for a reason that you might have spotted by yourselves, but now we make it explicit. So omega I prime is equal to omega j d partial xj partial y I. This is not a differential form yet, because on every point of the basis we are associating with every point of the basis we are associating the entire fiber, which is the entire space, and a differential form is a section. So a differential form is the case where with every point of the manifold you associate just one element of the tangent space to that point, which means that this omega I will be a function of x. So again, you have M, the base, then you have fibers, which are tangent spaces, and then you have a section, differential form of degree 1 or 1,4. So this one is called 1,4. Locally, omega is equal to omega I of x dxi, summing over I, of course, and then when you have intersections of charts, you do what is written here to switch from one set of coordinates to the other set of coordinates and then move on along the other chart. So a differential form of degree 1 is a section of the cotangent bundle. Since it's made a linear combination of differentials, and the differentials are elements of the cotangent bundle, which means they are linear maps acting on derivations, vector fields, and returning real numbers. Let's calculate what happens when we use that form and want to act on a vector field. So the differential form is this. I will not specify all the time that omega is a function of x, because we will always use sections, vector fields, or differential forms. Let me say that x is this. So it's understood that omega I and ai are functions of the point. Okay, but maybe for the first times, let's make it explicit, because I see it here. It's explicit also in the last year notes. So for a few times we do it, since we just introduced the concept. And then what is omega of x? that is omega I of x differential dxi acting on aj, let's say, partial over partial xj. What is a differential on this? Let's recall that this can be taken out at no price, because we proved it when we defined it. Or maybe I forgot to prove it. Yeah, I think I forgot to prove it. It's a simple consequence of the definition, which is this one. Note the following thing. df of g, a function times x, is, well, g times x is another derivation, so instead of x you have gx f, which means that this is g times the differential of f acting on x. So g goes out immediately, which we can use now here. This goes out, and so you have omega I of x, aj of x, dxi acting now on partial over partial xj, and that's the delta ij, so you have just a contraction of the components. And that's the action of a differential form on a vector field. Now we can define differential forms of arbitrary degree. So we can say that a function defined on the manifold is a differential form of degree 0, of course. We define wedge. This symbol is not a lambda, is a wedge to the power s tm star. Let me check whether, yes, tm star is the fiber bundle. So this is a wedge product of the fiber bundle S times with itself, which is another fiber bundle, but in another topological manifold. So this space is the space of the anti-symmetric forms of degree S. So let me recall that lambda is equal to wedge. It's not a lambda, it's a wedge. What are these objects? The anti-symmetric forms of degree S. So first we give the definition in the simplest case, S equal 2, and then it's easy to give the definition for every S. In case S equal 2, we can always proceed as previously. We give the definition locally, and then the rules for the change of coordinates will apply to all the factors of this product. Wedge is a wedge product, so it's sort of product. And then you have the definition on the entire manifold. So locally, you have a set of components with two indices with a symmetrization factor 2, which can be sometimes used, sometimes not used, depending. It's just you can incorporate it into the definition of omega ij if you want, but let's use it for the moment. You write the two form this way, okay, with two differentials separated by a wedge. Many times the wedge will never appear, so it will be understood if you find it missing. That's what it is. And this is a map that acts on the product, Cartesian products of two tangent spaces. So a pair of derivations instead of one vector field, a pair of vector fields, and goes into R. Precisely like one form acts on one derivation and gives you a real number, omega 2. So if these are two derivations, and we could also, yes, define them as vector fields globally on the entire manifold, then you can have an object which is omega 2 acting on both, and that is a real number. What real number? The one that is given by this. Sufficient to specify how the wedge of the differentials dxi, dxj acts on the pair. Let me use local coordinates as usual, and the components of x and y will be denoted by ai and bi. Then this action is given by the determinant of what? Dxi acting on x, dxi acting on y. This is anti-symmetric, as we said at the beginning, so it must be something anti-symmetric. A determinant is good for that. And then you repeat the same row with xi replaced by xj. What is the result of that? That is the determinant dxi on x, dxi on this. Since it is a delta on this, it is just the ith component, ai component. So ai, bi, aj, bj. Then you take the determinant and you have ai bj minus aj bi. Therefore, when you act with omega 2 on xy, with this object, if you want to compute this object, you just apply the definition. That is to say, you multiply this thing by the factor there in front, omega ij divided by 2. Note that omega ij must be a anti-symmetric matrix. So omega 2 xy is what? Omega ij divided by 2 times ai bj minus bi aj. So it's even simpler with this notation. You just contract the two vectors with the tensor, which is the differential form. And similarly for differential forms of any degree S, S, you will have locally something like this, 1 divided by S factorial. Here I put this normalization factor S factorial to simplify the result. Here you see you have 1 after the contraction, but in a moment we will forget about it because it's not very practical for other users. So the components will be matrices with completely anti-symmetric matrices with S indices, depending on the point, and that will multiply the wedge of S differentials of the basis of the cotangent space, where the action of this wedge of differentials, well, the action on what? On a set of S derivations of vector fields, that will be equal to a determinant, again, of what? dxi1 capital X1 dxis capital X1, and then up to dxis capital X1 dxis capital XS. And again, when you can make this calculation, you will have S factorial elements when you act. You take omega S acting on this, and the S factorial will cancel this one. But similarly, sometimes you can consider a symmetric product, a space of symmetric forms. They are not called differential forms, they're called symmetric forms. They are not particularly used. One very famous example is the metric tensor in gravity, so that's a 2 form, but aside from that, this notion is not frequently met. So it's written something like that. Instead of a wedge product, it's a symmetric product denoted by this symbol, a circled X. And this denotes the space of symmetric forms of degree S. What does that mean? Well, locally, very similarly, you have omega S will be equal to, yes, let me specify these indices are, this object is completely anti-symmetric. Here instead you have an object that is completely symmetric. And it multiplies some formal thing that is written like this. Which again is an object, omega S, acting on a string of S vector fields, and so it's sufficient to specify how these objects act on such a string. It will not be a determinant, of course, it will be some symmetric combination, but aside from that, it is quite straightforward. We just gave the example which is most useful, which is s equal 2, because then it generalizes immediately. S equal 2, we can so we have dxi times dxj acting on a pair of vector fields as before. X is equal to ai partial xi, y is equal to bi partial divided by partial x I, and then by definition that is ai bj plus aj bi. So if you have a 2 form like we will see the metric, some 2 form with the coefficient gij divided by 2, because we want now to use this notation, then you multiply, this must be symmetric, and so you have gij ai bj. So from now on we will mostly focus on differential forms, which are the most interesting things for differential geometry. One operation that allows us to jump from one space to another for changing the degree S is the exterior derivative. Exterior derivative is a map that acts on the wedge product of M, the space of differential forms of degree M, and returns a differential form of degree M plus 1. It raises the degree of the differential form by 1 unit. How does that happen? So let me give you the local formulation, but I changed the notation with respect to before, because now I do not want to divide by s, or here it's m factorial. And in a while I will also suppress the wedge, because it's annoying to write all the time a wedge between the dx. D omega is the differential form which is locally defined by this, and then in the intersections transforms as easily as can be easily inferred from the definition. It is like this: you differentiate the components one time and add the corresponding differential to the left. So again, this is a meaningful definition all over throughout the manifold, which can be easily checked by working out the transformation properties which are induced by the transformation properties of omega, and the fact that this is just a derivative. We will not do it, but maybe you can do it by as an exercise. By the way, for the exam, you will have some. I will give some simple exercises like this, complement derivations, and you will give me the solved exercises before the oral examination. What is the interesting thing here? Then if you have problems, you can ask me. But basically, you know that when you differentiate something and you want to transfer, probably I've seen in other courses, transfer the good transformation properties from the object to the differentiated object. It's not enough to differentiate, you have to define a covariant differentiation, a covariant derivative, not here, because these are forms. Everything works automatically, no need to covariantize anything. So try, but we will see it in many other situations later. So, but for the moment you can try and see what you get. So the covariant derivative will be defined, I think, next time, yes, not today. But in the case of the good thing about differential forms is that you can differentiate them without any regard to these kind of things. And that is encoded into the anti-symmetry of the forms. A very important property of the exterior derivative is its nilpotency. The exterior derivative of an exterior derivative is identically zero. And that is easy to show because we have seen that d omega is equal to d I omega I1 I m, I think, dx I dx I1 dx I m. When you differentiate it another time, you have another derivative and another differential. dxj, dxi, dxi1, dxim. But this is zero because this object is symmetric in the exchange, with respect to the exchange of I and j. But this object, if there is a wedge that they don't write every time, this is anti-symmetric. So that is identically zero. This differential form omega is closed if d omega is zero. If its exterior derivative is zero, the form is said to be closed. Locally, it means that d omega is 0, so this object must be identically 0. But be careful before writing what the result looks like, because you have to recall that this is completely anti-symmetric. So locally, you have to take that derivations, the derivative of those components, but you have to completely anti-symmetrize in I1, Im. That is the condition. So for example, omega equal a one form, omega I dxi, d omega is dj omega I dxj wedge dxi. D omega equals 0 means di omega j equal dj omega I. It means that this object must be symmetric because it multiplies something that is anti-symmetric. But you cannot say that separately this is 0. So this is the condition curl equals 0 that you are familiar with from electrodynamics. So that means this condition, precisely. Now you might remember that in classical electrodynamics, when you have this condition, you conclude that there must be a potential such that E is minus, by convention, the gradient of that potential, which would mean EI equals minus partial I. Partial I think it was understood is a shorthand notation for partial divided by partial xi. V. And let's check what happens of the differential form if we insert this condition. So omega I is EI, but EI in this case is this object. Well, this is the differential of the function V minus. So omega in this case is said to be exact. Not only closed, this condition says omega is a closed differential form if d of omega is 0, but if omega is d of something else, it's said to be exact. There is a question mark here because the question is, when is that a differential form that is closed is also exact? Well, usually always in classical electrodynamics, but that is not true. So let's give the definitions before moving forward. A differential form omega, yes, of degree k greater than 0 is exact if there exists alpha, differential form of degree k minus 1, such that omega is equal to d alpha. So you have an exterior derivative that is a very important operation because it's nilpotent. The nilpotency allows you to play with it this way and define closed forms, which are those that are annihilated by the exterior derivative, and exact forms, which are those that are equal to d of something. And before pausing, let's observe that an exact form is always closed, but not vice versa. So if it is exact, it means that omega is d of something else. I want to prove that it is closed. That is to say d omega is equal to 0, but that's obvious because d omega is d of alpha, and d squared is 0, because d is nilpotent. So an exact form is always closed. The question is a closed form always exact? And the answer is no, which is why in the case of the electric field I have put the question mark. And a closed form is not always exact, but it is always exact in Rn or an open subset. So locally, in every chart, it is exact. Which is why in electrodynamics you don't care, because normally you work in Rn. But that's not true, because you can find configurations where you are not really working in Rn. So let's pause here, and in 10 minutes we start again.